Hello everyone, my name is Brandon Merfeld, and today we'll be examining the difference in body fat percentage and fat-free mass estimation in athletes based on the selection of body density equations. So for a little bit of background, when assessing and monitoring body composition, it can be a very useful practice to make adaptations to your training, as well as maintaining a certain performance and also reducing injury throughout an athletic season. Several approaches have been used to estimate body composition, with the most common being the two-compartment model, which separates the body into fat mass and fat-free mass. In conducting body composition analysis, there are many variables that can affect the results as they relate to body fat percentage and fat-free mass. So the purpose of this study was to examine differences in body fat percentage based on the selection of body density equations. The picture below just helps represent the two-compartment model a little bit better with a pictorial image of it, and we have the fat mass and fat-free mass divided. So for our methods, we had 88 male Division III athletes and 83 female Division III athletes come in for preseason testing for body composition. The data represents the mean, age, height, body mass, BMI, plus or minus the standard deviation. Body density was assessed using air displacement plethysmography, more commonly known as the BOD-POD, and this was used to create a two-compartment model for body composition as a part of preseason assessments from 2015 to 2020. The student athletes were asked to have no physical activity and food for greater than 24 hours and 8 hours respectively. 3 prediction equations were used to estimate fat-free mass and body fat percentage, which come on the slide below. So these are the body density prediction equations. First we have the Lohman, which has a separate prediction equation for males and females, which differs it from the Brozek and Siri. As you can see, they basically have the same basic structure, but it's very interesting to see in the results how much they differ based on these prediction equations. So as you can see, in the males, the Lohman has a statistically significant difference compared to the Brozek and Siri equations. In males, the Brozek and Siri equations are very similar, but in females, we can see that the Lohman, Brozek, and Siri body fat and fat-free mass are all statistically significantly different. So in the females, pairwise comparisons indicated that the Brozek equation resulted in higher body fat percentage compared to the Lohman. The Lohman equation resulted in higher body fat percentage than the Siri equation, and the Brozek equation resulted in a higher body fat percentage than the Siri equation. And as you can see, these were done using the body fat percentage plus or minus 1 standard error, and also the 95% confidence intervals. Similarly, in males, the Brozek equation resulted in a higher body fat percentage compared to the Lohman equation. The Lohman equation resulted in a lower body fat percentage value compared to the Siri equation, while the Brozek equation resulted in a higher body fat percentage value than the Siri equation. As you can see, we also have the body fat percentage plus or minus 1 standard error. We also are comparing them using the 95% confidence interval. So for our discussion, we decided that the densitometry-based calculation of body fat percentage and fat-free mass appears to be influenced by the prediction equation used. Caution should be used when using the different prediction equations to track changes in body composition over time or when comparing this to scientific literature. So for limitations, we did have to use the two-compartment model of body composition. This also assumes that constant density and hydration of the fat-free mass. Obviously, we tried to control this as much as possible with the eating and drinking policies noted before testing. And we also had to use the predicted gas volume instead of the average thoracic gas volume. As you can see in the picture below, this is how you would calculate the average thoracic gas volume, but with COVID, we felt that using the mouthpiece would not be very appropriate. Then here are my references. Then lastly, I want to finish with some acknowledgements. I want to thank Dr. Andrew Jagum and the Mayo Clinic Sports Medicine Research Department. I want to thank Christopher Dodge and the EWL Exercise Sports Science Department. And I also want to give a shout out to my fellow research assistants, Abby Ambrosius and Chingun Kurlbatter. Thank you guys so much for listening.